So now we're going to talk a little bit about hypothesis testing. This is getting into our inferential statistics. We're going to now be doing a little research or trying to test some claims that we or others are making. So here's some statements we have. I don't believe that the actual normal average temperature of a human is 98.6 degrees. I go to the store and buy some pop, and I don't believe that the actual average fill of a bottle of Coke is 20 ounces. And I don't believe that the actual proportion of people that smoke at LCC is 22%, as some have claimed. So what are we going to do? This is where a hypothesis test will come in handy. Hypothesis testing involves a few steps. First, we're going to make some claim. I don't believe that the bottles are filled to a certain level, or we can take an assumption or some claim that someone else has made. We're going to find some data, and then we're going to see what the data says. So, statistics is about testing assumptions. For example, if I have a coin and I flip it 1,000 times, I'm assuming the coin is fair, not weighted. I flip the coin 1,000 times, I get 995 tails. Well, given that the probability of that happening is very low, maybe my assumption of a fair coin isn't a good one. Maybe, in fact, the coin is unfair or weighted. Doesn't prove it, and the probability of getting 995 tails is very incredibly small, but it is still possible. I could get 1,000 tails or no tails. But when we make certain assumptions, if an event occurs such as 995 tails, maybe the assumption of a fair coin isn't a good one. So, with a hypothesis test, what we're going to do is say, for example, with the temperatures, we're assuming that the average temperature is 98.6, but say we get a sample of 2,000 people and their average temperature is really high or really low. Maybe that assumption of 98.6 isn't a good one. And our hypothesis test has shown us that, well, maybe there's some evidence to support my claim that the average temperature is in fact lower. So, how does a hypothesis test work? The first thing we need to do is determine a null hypothesis and an alternative hypothesis. I'm going to use the example of the temperatures. So the null hypothesis is the status quo, or what we've always assumed to be true, and that's that the temperature is 98.6. When we do our hypothesis tests, the null hypothesis will always include an equal sign. So in this case, for example, the mean equals 98.6. The alternative hypothesis is typically the claim you're trying to show is true, or some counter claim. So my claim in this case is that the average temperature is in fact lower than 98.6. So that's my alternative hypothesis. The alternative hypothesis, when stated in numbers, contains a non-equality, so a less than, greater than, or not equal to sign. The next thing we do is determine the level of significance and find critical values. So for significance level, basically we're talking about, we'll use the level of 0.05 or 5%. What this significance test, or this level of significance for your test, means is that we're saying 5% of the time we are going to reject a null hypothesis that is true. So this is our error. If we think about the justice system, the null hypothesis is innocence, the alternative hypothesis is guilt, and as a prosecutor, what you're trying to do is find evidence to reject the null hypothesis or reject innocence and show that in fact innocence isn't a good assumption to make. What happens is, guilty people are convicted, innocent people are acquitted, but sometimes innocent people are found guilty, and likewise guilty people are found innocent. So our level of significance means we understand that sometimes we're going to reject a null hypothesis that's actually true, and how often are we going to do that? In this case, or in most cases, we'll use 5% of the time. The critical values are the values in our distributions for either our t or for our z, which are the values that separate 95% of the distribution from the 5% that we're going to use to reject our null hypothesis. So for example, we've said in a z distribution 95% of the data is between 1.96 standard deviations and negative 1.96 standard deviations away. For a hypothesis test with a level of significance 0.05, those would be my critical values. Any samples that I get that are beyond 1.96 standard deviations away would be samples that are odd, which might lead me to reject a null hypothesis. Calculated test statistic. Really, this is the only thing that changes from hypothesis test to a hypothesis test. Say that 5 times fast. The test statistic really is simply the number of standard deviations a sample is away from the assumed mean. So when I calculate a test statistic, I'm finding out the sample of data I chose, how many standard deviations away is that sample from its assumed mean. And if it's very high or very low, this would be one that a test statistic that would lead us to reject a null hypothesis. And the last thing we do is we make some statement about the null hypothesis. We either reject it or we fail to reject it. And there's some statement that can be made. So for example, with the temperatures, if I reject the null hypothesis, I can say I've got evidence to reject the null hypothesis of 98.6 being the mean, and in fact it may be less than 98.6. Or I can say I fail to reject the null hypothesis. I don't have enough evidence to show that the mean is anything other than 98.6. So let's do one. The claim has always been that the normal temperature of a person is 98.6. We collect some data, find a sample mean, we find a standard deviation, we have a large n here, so we're going to do a hypothesis test for a large mean. Step 1, find the null and alternative hypotheses. So we've got the null is the mean equals 98.6, that assumption, the status quo. The alternative is the mean is actually less than 98.6. We'll use level of significance of 0.05, and from that we find a critical value of negative 1.645. And what that means is to the left, or less than negative 1.645, we have 5% of our normal distribution. And values below that, or further away from the assumed mean than negative 1.645, would be ones in our so-called rejection region. And then we'll calculate our test statistic. And we get negative 2.94. So nearly 3 standard deviations below the mean. So our interpretation, well, since the test statistic is less than the critical value, we will reject the null hypothesis. So it seems we have evidence to show that, well, maybe in fact our assumption of 98.6 isn't a good one, and in fact perhaps the average temperature is lower than 98.6. Again, remember, we prove nothing. This does not prove that the average temperature is less than 98.6, we just have evidence to support the fact that maybe our assumption isn't a very good one, because the probability of getting a sample with a mean that low, the probability is relatively small. Let's do another one. Here's our claim of Coke bottles not being filled actually 20 ounces. So we'll get some, we get some bottles of pop and measure their average fill, and we find a mean, a standard deviation. Since our n is smaller than 30, less than 30, we're going to do a hypothesis test for a mean with small n. Again, we'll find our null and alternative hypotheses. Mu equals 20 or mu not equal 20 is our alternative. Again, noting the null always has the equal, the alternative has a non-equality, an inequality, less than, greater than, not equal to. Level of significance and critical values. Again, we'll use 0.05, meaning 5% of the time we're going to reject a true null hypothesis. Critical values will be plus or minus 2.069. Looking at the t-distribution, we'll find 4.025 in each tail, n minus 1. At degrees of freedom, 23 degrees of freedom, we find the value of 2.069. We use positive or negative because 2.5% is to the right, 2.5% is to the left. Calculate our test statistic, which is negative 0.74, which basically means this particular sample of 24 bottles with its mean is roughly 3/4 of a standard deviation away less than the assumed mean. And because the test statistic is not outside of the critical values, we fail to reject the null hypothesis. That doesn't mean the mean actually is 20. We just don't have enough evidence to show that it isn't 20. Okay, we'll do one more. That's it. Claim for our smokers. We do a survey, we get some data. We're going to do a hypothesis test for a proportion. So here we've got P as our parameter that we're doing a test on. So the null is that it's the 22% as claimed. The alternative is our claim that it's more than 22%. Again, our critical value and significance level 1.645. Since we're doing a one-tailed test, right-tailed test, 5% of the distribution is to the right of 1.645 or greater than 1.645. And our test statistic is negative 1.22. Our sample proportion happened to be 18.8%. Well, again, since the test statistic is not greater than the critical value, we fail to reject, and we don't have evidence to show or to support our claim that more than 22% of people smoke on campus. In conclusion, as you'll notice going through these hypothesis tests, they're all set up the same way. The only thing really that changes is that particular test statistic that you use. For a large mean, large N mean, you use a z-distribution and a test statistic labeled z, though it's just value minus mean divided by standard deviation over square root of n, which is the same calculation-wise for the mean for small n. The only thing that changes there is you use a t-value, a t-critical value, as opposed to a z-critical value. And for a proportion, you have its using critical values from the z-distribution, and you're calculating a specific proportion test statistic. And that is hypothesis testing.